Okay, good morning everyone. I think maybe we'll get started. So welcome to Linear Algebra 2. If you weren't expecting Linear Algebra 2, either at least one of you or I is in the wrong room. So I'll start off just with a few practical bits of information. So this is Linear Algebra 2, which is building on from Linear Algebra 1 that you saw last term. So we're meeting Mondays and Wednesdays from 10 to 11 a.m. and that's always in this room L1. So since you're all here, you've probably understood the timetable okay. And one thing to note is that this is just a short course. So we're only having lectures between weeks 1 and 4. As you saw in Linear Algebra 1, the idea of linear algebra is really to study maybe functions which have the property that f of ax plus by is a times f of x plus b times f of y. And here maybe I'm thinking of x and y as being vectors and a and b as being scalars. But you could also imagine slightly more general situations where this is true. And any function that satisfies this, we're calling linear. And then linear algebra is the algebraic study of these sorts of functions. And it turns out that this is one of the most important and well understood areas of mathematics. So there's a very beautiful theory of this. And one quick summary is you can understand a lot about this by looking at matrices. And vector spaces, so objects that we've encountered in Linear Algebra 1. And actually, a huge amount of modern mathematics is often to take some very complicated situation and to try and maybe approximate it in some way by some linear system. So when you do calculus, you're approximating a more general function by something that looks linear on a small scale, and linear algebra really lies at the very heart of a huge amount of mathematics. You've maybe already seen that linear algebra has various different applications. If you want to solve simultaneous equations, you can cast this as a problem in linear algebra, just as you can understand linear algebra as looking at vector spaces and more geometric problems. And one philosophy for the way that I like to think about linear algebra that I think would be useful in this course is to, when you're thinking about statements, to always imagine them geometrically as questions about 2x2 matrices and transformations of the plane, but to always write down proofs and arguments much more abstractly using algebra. So think about linear algebra geometrically, in particular as, say, transformations of the plane. So I'm not too good at visualizing things in 3 dimensions, but I can visualize things okay in 2 dimensions. And often it's very easy to visualize things if you just imagine that everything is some operation on the plane. So I like to think about what's going on in a sort of geometric way, but we're going to prove rather more general statements. And one of the big powerful things about linear algebra is you can take this geometric intuition, but then write down formulae that work in arbitrary dimensions in a very nice way. And often the algebraic way of doing the calculations is much, much more convenient than the geometric way, even if maybe we were originally motivated by the geometry. So I want to do calculations and proofs abstractly using algebra. So if you do it this way, the proofs and the statements often hold in much more generality, but also it's much more convenient to do the calculations in this way. And okay, so I've maybe said this in very vague terms. Maybe we can sort of think about a concrete example as to how this might work. And this gets us to the first thing that I'd like to talk about in linear algebra, which is determinants. But I'd like to demonstrate it through this sort of philosophy. So think of just some linear transformation of the plane So what do I mean by this? Well, some combination of rotation or stretching in one direction, or maybe I could skew it if I shift things. But a linear transformation is going to preserve lines, and I can think about just taking the unit box, and this will then be mapped to some maybe skewed box, so it'll be some sort of parallelogram, and maybe the axes won't be horizontal anymore. And I want to understand transformations like this. So this is just the unit square in R squared, and then this gets mapped to some parallelogram. And the unit square has area 1. And this parallelogram, the area won't necessarily be preserved. So we'll have some different area C. But I can think about the linear transformation acting on other shapes. So I could have maybe a triangle, and then so that will get mapped to some strange skewed triangle or something. And maybe I can draw some triangle with area 2. And it's a fact that the image of the triangle would then have area 2c. So you can, it's an exercise if you want to work this out. And in fact, or maybe we would guess just from doing a couple of examples like this, that every shape, well, I'm not going to be precise about what I mean by shape, has the area scaled by a factor of c. So often it's unwise to make a general guess just from doing 2 examples, but you can do a few more examples if you like. And it turns out this guess is true And this constant c is going to depend on the linear transformation. And this constant c is essentially the determinant of the linear transformation. So it's clearly going to be some important property of any linear transformation that it turns out that even if you're working in many dimensions, any reasonable shape has its volume scaled by a constant factor, and this constant factor is called the determinant. So this is very much what I mean by thinking about things geometrically, but it turns out that it's really quite difficult to make lots of this precise, and the calculations get a bit horrible if you try and think about things just in terms of volumes. So very much in the spirit of this philosophy, I want to do calculations trying to abstract out properties of this. So let's think about a few properties of this scaling areas would have in R squared, and try and think of, if I can write these down as abstract properties, maybe I can understand properties of this linear transformation just from these abstract ideas. And so note that the area or volume of a linear transformation is linear in terms of the entries of the linear transformation. So maybe let's consider a matrix. So let A be a matrix with columns A1 up to AN. So these are, we can think of these as just vectors in R to the n. So A is an n by n matrix. And the volume of the image of maybe the unit cube in R to the n is linear in the columns. So the volume of so maybe a nice way for me to write this is whenever a matrix has columns A1 up to AN, I'll write this as A is equal to square brackets A1 up to AN. And the volume of some columns, and if in the jth column I have a vector bj plus cj of the unit cube is equal to the volume where I have the same columns with bj plus the volume when I have cj as the jth column. And this is basically based on the idea that if I have two vectors here, A and B, so I'm thinking of this as, or maybe to stay consistent, I'll call this B and C, the area of this is equal to just the area where I have vector B plus C here. And so if that was A, then I'd have just A here. So that's one property. A second and easy property is that if AJ is equal to AK for some j not equal to k, so if two of the columns are the same, then the image of the unit cube will collapse. So maybe it's easiest if we just think about this, for two consecutive columns. And then we don't need to worry about this. So if I have two consecutive columns which are exactly the same, then the volume of the image of the unit cube is equal to 0. And so again, I'm really thinking about this, and if I have two vectors being the same, then I will just have two columns aj and aj plus 1, and the whole unit cube will just degenerate down to a line. And then a third property that we get from just looking at transformations on R squared is that the if A is the identity matrix, then it preserves the unit cube in R to the n, and the volume equals 1. So I haven't necessarily proved any of these statements, but maybe they're all believable. And so what I want to say then is that these are properties that this determinant, I think, should satisfy, and these are all algebraic properties. And therefore I want to study the determinant just through its algebraic properties. So this is going to study the determinant, we're then going to define what it means for any map to be determinantal, which means it's going to satisfy the equivalent of these properties 1, 2, and 3. So we're now going to start doing some concrete mathematics. Maybe before was some geometric motivation. So we're going to say, if I take any function, so I'm thinking of a function d, and it's going to take as input n by n matrices with real entries, and it's going to output some real value. And I'm going to call this map, I'm going to say it has the property of being determinantal, meaning it behaves like what I expect this determinant to behave like if it satisfies the analogous properties. So if I think about my map acting on some matrix where I'll write it in the column form, and in the jth column it has the vector bj plus cj, then I want it to be equal to the determinant at bj plus the determinant at cj. For any choice of column index j between 1 and n. And similarly, I want it to scale. So if I scale one column by a factor lambda, then I just want this to scale the determinant by a factor lambda. So this is going to be the first property, and I want this to be d is linear in each column. So this is basically the property that we guessed the volume of the image of the unit ball should satisfy for any linear transformation. The second thing is that I want D to have the equivalent of the second property here, that if I evaluated at some matrix and two of the columns are equal to each other, maybe two consecutive columns, then I want the determinant to be equal to 0. And then the final thing is if I evaluate the determinant of the identity matrix, I just want this to be equal to 1. So this is a completely abstract definition of what it means for any function on matrices to be determinantal. And at least based on this motivation, we expect that the volume of the image of the unit cube should satisfy this. And so we think it should be an important property of any linear map, but now this applies in general to matrices in an algebraic way. So the first thing I want to do is to show that if any linear map satisfies these properties, then it actually satisfies slightly stronger versions of these properties. So we can automatically upgrade it. So proposition, if D is a determinantal map, then 1, I can swap two columns if I switch the sign of the determinant. So D is alternating in the columns. So D of some matrix with columns bj and bj plus 1 is equal to minus the determinant of the same matrix if I swap the columns. So swapping to just changes the sign. A second property is that, okay, I said the determinant is equal to 0 if two consecutive columns are the same, but actually they don't have to be consecutive. So if I evaluated at some matrix with two columns bj and bi, this is 0 if any two of the distinct columns are the same. And then a final property is a stronger version of it being alternating, that the first one was saying it's alternating in consecutive columns, but actually I can do it for general columns. So if I swap any two columns, So whenever I swatch any two columns, I just get exactly the same answer, but with the opposite sign. So let's go ahead and prove this proposition based on the properties that we've defined for a determinantal map. So let's start off with part 1, because that really holds the key to the whole thing. And what I want to do is to think about D being evaluated where I'm evaluating the jth column and the j plus 1th column at bj plus bj plus 1. So here, this is the jth column, and this is the j plus 1st column. J plus 1th column. So by linearity, I can expand this out. So what do I get? Well, I'll get one term with bj and bj. I'll get one term with bj and bj plus 1. I'll get one term with jth column bj plus 1 and j plus 1st column bj. And then I'll get a final term with jth column bj plus 1 and j plus 1st column also bj plus 1. So this is property 1. But by property 2, we have that the left-hand side is equal to 0 because it has the jth column and the j plus 1st column being the same. So I'm just using this property. But moreover, we also have that in my expansion into 4 terms on the right-hand side, the first term and the last term must also be 0 because these also have 2 columns which are the same. And so if I substitute these being equal to 0, I therefore find that this is 0, this term is 0, this term is 0, and so I just get the sum where I have jth column bj and j plus 1st column bj plus 1 is equal to the negative of exactly the same thing where I swap the 2 columns. And so this gives the first property. So for part 2, I can now just repeatedly use part 1 to move column J next to column I, and I change the determinant just by a factor of plus or minus 1. But then the determinant has to be 0 because I would have 2 consecutive columns being the same. And so that instantly gives the final property. And so for now, for the third part of part 3, there's a few different ways I could do it. But I can essentially follow exactly the same proof as part 1. I can think about evaluating my matrix where I'm now evaluating it with columns bi and bj in position I and bj plus bi also in position j. And I can follow exactly the same argument as for part I. I can expand this out as 4 terms. This left-hand side must vanish because 2 of the columns are the same. And by part 2, I've seen that whenever 2 columns are the same, the whole thing vanishes. But then when I've expanded it out, the first term and the last term must also vanish. Using part 2. Okay, so far what we've seen is that we've maybe had this geometric guess that there's an important property of any matrix or linear transformation, which is how it scales volumes. And this is an important constant that you associate to any matrix. I've then defined this abstract property of any function being determinantal if it satisfies various of the properties that we expect this genuine constant to satisfy. And I've seen that if it satisfies those properties, then through this proposition, it actually satisfies slightly stronger versions of those properties. So we've now done enough of the basic important properties of the determinant, but we haven't seen that actually there's any such map that satisfies these properties. And so that's what I'd like to do now. I want to show that there is at least some function which satisfies all these properties. In the back of my mind, I'm thinking that a function that satisfies these properties is the volume of the image of the unit cube. But again, I don't want to do any calculations geometrically. I want to do them all in an algebraic way, because that makes everything much, much cleaner. And so this is maybe the first important result of the course. So let's call it a theorem. A determinantal map exists on n by n matrices exists for each n bigger than or equal to 1. So it's not totally obvious that something should exist from this. And to prove this, I want to do a proof by induction, where I'm going to induct on the size of the matrices. Okay, so let's first of all start thinking about the case when n equals 1. So we're just looking at 1 by 1 matrices. And I can define D of just a 1 by 1 matrix A to be maybe the most obvious thing, just its entry A. And since the identity function is certainly linear, it's very easy to check that D satisfies the properties 1, 2, and 3 here. Okay, so we've shown that something exists for 1 by 1 matrices. And now we want to consider the case when n is bigger than 1, and we're going to assume that something exists, some determinantal map exists for n minus 1 by n minus 1 matrices. So we somehow want to construct a function on n by n matrices out of this function that we're assuming to exist on n minus 1 by n minus 1 matrices. So I want to cook up some way of coming up with a determinantal map that satisfies those three properties, but I want to somehow use this n minus 1 by n minus 1 map. So I want to think of some matrix A, which is an n by n matrix. So let's say it has entries little a ij. And if I'm going to use this dn minus 1, which is clearly going to be important in the argument, I have to think about how can I construct a n minus 1 by n minus 1 matrix out of this n by n matrix. Maybe there's one easy way to do this, which is just to throw out some row and some column. So I want Aij, capital Aij, to be the n minus 1 by n minus 1 matrix formed by removing the ith row and jth column of A. So this is one way of constructing various different n minus 1 by n minus 1 matrices from my n by n matrix A, and I'm now going to consider, so let's choose some I between 1 and n, and I'm going to define my attempt at a determinantal function on n by n matrices as follows. So I will put minus 1 to the I plus 1, a I1, and then I'm going to use the n minus 1 by n minus 1 function on the matrix AI1. But maybe, so this is some function that would work on n by n matrices, but is ignoring lots of the elements in the ith row. So instead, I want to add lots of these similar versions of this together to get something that's sensitive to every single element in the matrix. And it turns out that a good way to do this is to keep on multiplying by minus 1 and just going through all the different possible choices in the ith row. Okay, so I've just plucked from thin air this matrix here, but I think if you play around with it a little bit and you decide that you want to come up with some way of defining a function on n by n matrices in terms of a function by n minus 1 by n on n minus 1 matrices that depends on each element, you'll see that actually this isn't such an unnatural thing that I've just picked out of the air. Maybe you wouldn't have guessed these minus 1 factors, but it should be clear once we go through a bit more of the proof why these minus 1 factors turn up. Anyway, I've defined this function, and this is a function on n by n matrices. And I want to show you that it's now determinantal, so I want to verify that it satisfies properties 1, 2, and 3. And if I've done this, I have completed the proof. Okay, so I'm just going to verify the properties in order. Maybe I'll move on to the middle board. I guess maybe it would be useful to keep this board up so that we can see what the properties are, so maybe I'll move over to the right-hand side. So let's start off with property 1. So we'd like to show that D is linear in each column. So since D is a sum of terms aij d n minus 1, aij, it is sufficient to show each of these is linear in the columns. Okay, so I just need to show that each of these different quantities aij dn minus 1 of capital Aij is linear in the columns. And so let's concentrate on the kth column of my n by n matrix A, and I'm going to consider these functions. So if j is equal to k, then aij doesn't depend on the kth column of A. Because this is formed by removing the kth column of A. But little aij is just the ith element of the kth column, and so it's certainly linear. And so by putting these two things together, we see that aij the n minus 1 of aij is linear in the kth column. When j is equal to k. What if j is not equal to k? Well, then we have that aij doesn't depend on the kth column at all, because it's just some other entry in the jth column. But we have that dn-1 aij is linear in the kth column of A, since we're assuming that this function is determinantal and so is linear in the columns. And therefore, in this case, we have the aij dn-1 of aij is linear in the kth column. And therefore, regardless of what value of j is, these functions are always linear in the kth column, and so d is linear in the kth column. Okay, so we've therefore verified property 1 for this function d that I've written down. So we're left to verify properties 2 and 3. So maybe we have just enough space here. So let's go for property 2. Imagine that in my matrix A, I have the jth column is equal to the j plus first column. And so I want to show that this determinant has to be 0 then. So again, it's going to look a little bit similar to this. Aij will have 2 columns the same, 2 consecutive columns the same, because it essentially has the columns inherited from aj and aj plus 1, unless we removed one of these two. Okay, sorry, my notation's slightly bad. Let's imagine that ak is equal to ak plus 1, just because otherwise I'll get confused by all the indices. Apologies. So imagine that the kth column is equal to the k plus first column, and now I'm looking at one of these matrices, aij, where I'm removing the ith row in the jth column. If I haven't removed either the kth column or the k plus first column, then whatever corresponds to these two will still be the same, and so we'll have 2 consecutive columns the same, and therefore I'll have the dn-1 of aij is equal to 0, but this is only true if I haven't removed one of those 2 columns. So if I didn't remove either of those 2 columns, then 2 of the columns will be the same, and so the determinant will vanish on these n-1 by n-1 matrices. And so this means that when I'm evaluating d at A, I would have loads and loads of terms, but virtually all of them are 0. I'm only going to get the terms from aik and aik plus 1. So I can write out precisely what this is, and I just get the 2 terms from when I have aik and aik plus 1. But then, if the kth column is equal to the k plus first column, I have that aik is equal to ai k plus 1, and little a I k is equal to little a I k plus 1. And so in particular, these two terms are equal to each other, and so the determinant vanishes. So now, finally, I just need to check property 3. So if A is equal to IN, then Aij is equal to 0 unless j equals I. And so all but one term in this huge expansion vanishes. And so I have this function evaluated at A is minus 1 to the I plus I, aii d n minus 1 of aii. But this is equal to 1 because minus 1 to the I plus I is 1, aii is 1 whenever I is the identity matrix. And by assumption of dn minus 1 being determinantal, this also evaluates to 1 at the identity matrix, which is what I get when I remove the ith column and the ith row. And so this means the function d satisfies properties 1, 2, and 3, and so I've shown it's determinantal. And so, therefore, by induction, we know that there exists at least one different determinantal map on n by n matrices. So, therefore, D is determinantal. And therefore, determinantal max exists. Okay, so I'll stop here. What we've seen is that there's this, we guess that there's this important geometric property of matrices, which is how they scale volumes. But it turns out that it's very messy to work with that, so we've abstracted this out to some algebraic properties, and then working with those algebraic properties, we've shown that there's something that exists that behaves in exactly the same way, and next time we'll show that this is in fact a unique map that has all of these properties. Okay, thanks a lot.